The second speaker today is Vaidika Pardhi. She is a Ph.D. student here. She received the B.Tech degree in Electrical Engineering from GGS College, Nanded, India in 2017, and M.Tech degree in Power Electronics and Drives from VNIT Nagpur, India in 2022. And she is currently working towards the Ph.D. degree in multi-level inverters for drive applications with the Department of Electronic Systems Engineering, IISc, Bengaluru, India. She has worked as a systems engineer with the Tata Consultancy Services, Pune, India, where she collaborated with Ford Motors, Pune, on electric comfort features. Her research interests include power electronics and electric drives, particularly in electric vehicles and multi-level induction motor drive applications. Okay, please welcome the speaker.
Good evening, everyone. My name is Vaidika Pardhi. I'm a PhD student here, and today I'm presenting my research topic on the switch capacitive 9-level inverters for the drives applications with sinusoidal PWM control, which works in the extended linear modulation range and also independent of the power factor. So moving further, it's a presentation outline which I'll first introduce fundamentals of the AC/DC drive systems, then conventional 2-level inverters, then modulation schemes, multi-level inverters, OEM drives, motivation behind this topic, then coming to the main topic, and it's inverter topology, its circuit, proposed circuit, space vector diagram, and how the circuit capacitor balancing happens in the circuit, supporting with the simulation and experimental results. And further, I'll conclude with the presentation. So this is a basic typical AC drive systems which allows the inverter to operate with a variable frequency and variable voltages. Also improves the efficiency. This drive systems which gives the dynamic control and flexibility for the controlling of the motor loads. So these are typical drive systems. Further moving, this is a 3-phase 2-level inverter, in which we use 3 phases, and it's, having a combination of it's 8 combinations of the switching pattern, having 3 legs. Each leg is having 2 switches which works in the complementary fashion, and there is 8 possible switching states. Also this works with the modulation schemes like sine triangle PWM, space vector PWM, and sine triangle space vector modulation technique. So I'll move to the further slide. Yeah. So here the switching states are highlighted, all the 8 possible combinations of the 2-level conventional inverter. Yeah. So now coming to the modulation schemes, first I'll discuss on the sinusoidal PWM. So here we are having a maximum phase limit till 0.5 DC link what we have sourced to the inverter. And for the space vector PWM, it's increased by the 0.577, means 15% more DC utilization we are doing. These are the modulation schemes that can be used for control of the inverters. So here the catch point is for the space vector PWM, we utilizes more the DC link. Our whatever the DC source we are giving as a source for the inverter, so we can more utilize that. So now moving here, there's some simulation results in which we have you can see that in figure first, the basic sine triangle here. Sorry. Okay. Yeah. So here in first figure, the carrier and modulating waveform, which is sinusoidal, it performs comparison, and inverter works. And when it is greater than the reference sinusoidal waveform, the top switch is on, and when it is less than the carrier waveform, then the bottom switch is on. So this is a logic implemented in the basic 2-level inverters. Now in the second figure, in where it's not working. So yeah, where the third harmonic is injected, and it the modulation scheme is same act as a space vector PWM there. So there in space vector PWM, I have said earlier also, we are increasing our utilization of the DC source. So moving to the next slide. Yeah. This is a space vector structure, how it for the two-level inverter. So basically, space vector structure is you will have the pole voltages levels of all the three phases, and it's denoted in the 2D diagram. So it's easy to calculate what are the voltage levels we can get for the output voltage through the inverter. So this is a diagram, and how that inverter works with the different switching states. So this is a table which shows that according to the different switching states, what are the pole voltage levels we can get for each phases. This is a table for that, and for all the active vectors, 1 to 6 are the active vectors, and 0, 2 combinations can give for the 0 vector. This is a 0 vector that in diagram. This laser is not working. Yeah, okay. So you can see that it's a hexagonal structures, and all the active vectors are all the vertices, like 1 to numbered from 1 to 6, and 0 vector is 0 and 7. These are the equations, supporting equations. Now what are the limitations? Why we are moving for the multi-level inverters? So first we will see the limitations for the two-level inverters. So for getting the sinusoidal current waveforms, which is very much needed for the motor loads, so we need a large filters, and also in two-level inverters there will be high dV by dt stresses on the switches. So this will impact the life of the switches. Also, there is a lack of fault tolerant capability. As you have seen that in two-level inverters, if one of the leg is got faulted, you have to shut down your system. And whenever, and most of the industries or applicable inverters applications are for the EVs. So if one of the switches get fault, whole systems have to be stopped down. So it's a limitation for the two-level inverters. And also it introduces a lower order harmonics, which causes a lot of pulsations in the current. So it's torque pulsation, which will hamper the motor life. So these are the limitations for the two-level inverters. So now motivation for the multi-level inverters. So multi-level inverters, we will get a reduced harmonic distortions, good waveform quality, and also the lowering the dV by dt stresses on the switches. And in multi-level inverters, we are distributing the stresses among various switches. So here the higher voltage capability using a low voltage devices. This combinations we can use for the high power and medium power devices. Also the power quality we can improve, and this multi-level structures we can implement for the modular and scalable structures like cascaded edge bridge, and also we can enhance the reliability of the system. So that's the motivation behind why we are going for the multi-level inverters. Now moving ahead, these are the few common topologies that we implemented for the multi-level inverters. That is diode clamped inverter topology, in which we are using a diode and switches combination to get a multi-level structure. This is a second one is a flying capacitor inverter topology. Yeah. And third one is a cascaded edge bridge. It's commonly used in the batteries and two-level inverters and the industrials. So the cascaded edge bridge, and with the switching patterns, how we will get the pole voltages. Pole voltages means each phase voltage is A and O. That's across the voltage. What are the pole voltages we can get from different switching patterns? So it's illustrated in the tables given below. So these are the basic topologies evolved in the multi-level inverters. Now moving forward here. Now the question will come, what are the modulation schemes and what are the modulation boundaries? So linear and over modulation boundaries. So linear modulation boundaries, in which we can get a maximum phase voltage using a space vector, is 0.577 VDC, and that's the inscribed circle in the hexagonal structure. Till then it's a linear modulation, and after that, that's the orange color boundary. It's extended linear modulation boundary. With two-level inverters, we cannot go to after that. So multi-level structure will give you the freedom to get the extended linear modulation boundaries. This what happens, lower order harmonic should not be there. If it is there, then torque pulsations will come in the motor. So now these are the points which makes the research on the drives which we can go for the OEIM, means open-ended induction motor drives, in which independently both the sides motor load is fed, and more utilization of the DC source can be done. Here again the harmonic harmonic distortion is reduced, and also we are enhancing the fault tolerance for the drives operation. So this is the OEIM drives, means open-ended induction motor drives. So now this is the introduction part. Why now the motivation behind the work is, as there are multiple isolated DC sources like batteries, so instead of multiple isolated DC sources, the point is it's very difficult to neutral point voltage balancing is difficult. So here now the need for the single DC source multi-level inverters, and also multi-level inverters, the components will increase. So in less component count, how we are going for the more voltage levels, that's the target. Reducing the switching losses, achieving the extended linear modulation range while maintaining the sinusoidal operation, reducing the device stresses, and using the switched capacitive filter for the secondary side. I have shown you the OEIM drive, which is also fed from the secondary side. So harmonic suppression should be done for the using the switched capacitive filter, and also maximum utilization of the DC source should be happen. So these are the motivations behind this topic. So this is a proposed circuit for the inverter. It is a 9-level inverter topology, and primary means left side it's a primary inverter, in which it's a 3-level inverter, and secondary side it's a cascaded edge bridge 3-level with a 2-level capacitive filter. Again, the source is single DC source. Secondary side, no DC sources there, only single DC sources applied in this circuit. This is a space vector structure formed for the secondary side, that will be the 6th level. This secondary side space vector structure can give me the voltage levels across the pole voltage is a 3 VDC by 8, VDC by 4, VDC by 8, 0 and VDC by 8. So the smallest one is VDC by 8, and we have seen that VDC is it's divided into the 8 parts. So 9 levels are formed in the output voltages. So this is a complete space vector structure for the inverter topology. So so here the linear modulation boundary is till the radius 0.866, which is it's RP. So it's a linear boundary for this topology, and for the extended linear modulation boundary, which is 0.955 VDC. So the points U, V, W, X, Y, Z, these are the extended linear modulation points which I have to switch to run my motor load to the base speed, means in the extended linear modulation boundary. So here in this we will get a maximum peak fundamental as a 0.367. That's the maximum fundamental we can get from an inverter. So now I have shown you the inverter topology in which capacitors are there. So many capacitors are there. So capacitor should be balanced at their reference value. That's very important. So how the capacitor balancing happens in the proposed circuit? Each capacitors are balanced. Secondary side is balanced using the space vector redundancies. Means the vector point, resultant vector, that's the resultant vector OD, that can be obtained using the 4 redundancies. That's the number, means with switching combination using the other ABC states. So these are the capacitor balancing states. These are the redundancy formed using all the 3 phases. using the space vector redundancies, and the primary flying capacitor is itself balanced using the pole voltage redundancies. So now coming to the simulation results, the first waveform is phase voltage at so variable frequency drives. This inverter topology is applicable for the variable frequency drives. So at different frequencies, the simulation results are taken, and after that supporting experimental results are taken. So at 5 Hz, 20 Hz and 40 Hz, these are the linear modulation range results, in which you have seen that the seventh trace, that's the sinusoidal currents are obtained. It's some current obtained using a motor load, and the D1 is a 50 Hz extended linear modulation range, in which we have again we got the expected our sinusoidal current. That's the target for this work. So here simulation results, and for the experimental setup, this is a flow diagram in which always the maximum deviated capacitor is giving a preference to charge or discharge to balance. So this is a experimental setup, and in the implementation block diagram for the experimental work. So this is the supporting experimental results in which you can see that from trace 4, 5, 6, these are the capacitor voltages which are balanced at their reference values, and that's what we got the proper pole voltages and phase voltages and the proper sine waveform. The transient results, like we have suddenly changed the load of the motor, means speed reversals we have done, and we have to see that our system should be stable in the transients and dynamics also. So these are the transient results, supporting results, in which capacitors are still balanced in transients also. This is a startup condition in which from dead start we have start our experiment, and no requirement of the auxiliary or pre-charging circuit, and independent control of each capacitors is done in this work. So these are the it's a comparison between the conventional scheme, which gives a 6-step waveform, and in where it works in the extended overmodulation region with lower order harmonics. This lower order harmonics we have suppressed in our proposed scheme. You have seen that all the lower order harmonics are absent there, and that's the XY plot, which is in first one it's a hexagonal structure, but it's a circular trajectory in the proposed scheme, which makes our current nearly sinusoidal, and absent of all the lower order harmonics that are not good for the motor load. So this circuit also work irrespective of load power factor. If it's a pure resistive load also, so the circuit works perfectly with all the capacitor balanced to their reference values. So it means this experiment is tested with the resistive loads, lamp loads, and we got the still maximum phase voltage with that. Comparison with few references and previous references, few other 9-level topologies. So switching losses is reduced in this topology because most of the switching is happening on the low rated inverter, not the main inverter. So and the motivation for our work that to reduce the switching losses, so it is achieved in this circuit, proposed circuit. So I'll conclude the presentation that the key outcomes from the work is hybrid multi-level inverter topology, which uses a cascaded structure of 3-level inverters with using a switched capacitor and a single DC source, not isolated DC sources, and extending the linear modulation range, capacitor voltage regulations throughout in steady state and also in transients, load power factor independent operation, and supporting all the experimental validations with reduced switching losses. Few references I have had. Thank you. And